strong and weak acids, strong and weak bases. So acids can be divided into strong acids or weak acids. Hydrochloric acid, HCl, and hydrofluoric acid, HF, appear to be very similar, right? Their formulas are similar. Chlorine and fluorine are both in the halogen group, but there's two very important differences. HCl is a strong acid, which means that it is a strong electrolyte. When you put HCl into water, the hydrogen ions and the chloride ions separate completely. You don't have any intact molecules left. HF is a weak acid. So it ionizes somewhat. It does produce hydrogen ions. It is an acid. But some of the molecules, in fact a lot of them, remain as HF molecules, but in solution. So strong acids ionize completely. Strong acids are strong electrolytes. And so strong and weak here are used in the same way when we're referring to acids or bases or electrolytes. So HCl, you put it in water, it separates completely. So here, the hydrogen and the chloride separate completely. The chlorides don't have any hydrogens hanging around with them. If you have a 1 molar HCl solution, 1 mole per liter of HCl, then that will form hydronium ions. So we look at this equation. Remember, hydrogen ions are just protons. They're like tiny babies. They're too small to be out by themselves. And so we don't just see hydrogen ions, we actually see the hydronium ions, which is that hydrogen ion being held by the water. So for every hydrogen ion in the HCl, we get 1 hydronium ion. For every molecule of HCl, we get a molecule of hydronium ion and a molecule of hydrogen ion. So if the concentration of the acid is 1 molar, then the concentration of the hydronium ion is 1 molar. When we put a formula in brackets like this, that means the molar concentration of that formula. So this brackets around H3O plus means the molar concentration of hydronium ion. When we write this equation, we use a single arrow, just pointing in one direction, meaning it goes completely to hydronium and chloride. Pure water doesn't conduct electricity. Now, tap water is not pure water, and tap water can conduct some electricity. So even though pure water doesn't conduct electricity, you still need to be careful when you're dealing with electricity around water, right? So you shouldn't be messing around with electricity standing on a wet deck or something, right? Because is the water that you're standing on pure? No, it's got all kinds of stuff in it. It's dirty, right? It's on the ground. That can conduct electricity and get a nasty shock. But pure water doesn't conduct electricity because there's no ions to carry the electricity. So if we hook a light bulb up and we take the wire connecting back to the socket and we separate it and make it go through the water, the light bulb will not light. If we put an electrolyte in here, sodium chloride is an electrolyte, or hydrochloric acid, which is a strong electrolyte, separates into ions. The ions will carry the electric current and the light bulb lights up. There are 6 strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. Sulfuric is a diprotic acid, meaning it has 2 hydrogen ions. It has 2 ionizable hydrogens. The rest of these are considered monoprotic. They only have 1 ionizable hydrogen. So there are 6 strong acids. All the other acids are weak. A weak acid does not ionize completely. So HF is an example of a weak acid. You put this in water, and a lot of it stays as an intact molecule. Only a little bit will actually ionize. So we look at the pictures here. We've got these molecules floating around. There's 3 molecules, and only the 4th molecule ionized. So it didn't ionize completely. Weak acids are weak electrolytes. They do form ions, but they don't form very many ions, and so they're poor conductors of electricity. The light bulb is going to glow weakly because it's a weak electrolyte, it's a weak acid. When we write the chemical equation here, we use a double arrow. We've got the arrow pointing in both directions because this is only partially ionized. It goes partly over here, but a lot of it's still over there. And so that indicates that the reaction is going both ways. So if we add a weak electrolyte, such as a weak acid, there are some ions, and so the light bulb will glow, but only very dimly. This is weak, as opposed to the strong acid. Here are some of the weak acids. There's a whole bunch of them. Anything that's not a strong acid is a weak acid. So if we look at these pictures, which one of these is illustrating a weak acid? Kind of have to look at them for a while to figure out what we're looking at. C. This is the weak acid. So we've got, and it helps that they labeled them here because otherwise this is just jumble of little balls, right? So here we have a hydronium ion. That hydrogen came off of one of these acid molecules. So here's the one that lost the hydrogen ion to the water. And the rest of all of these are the intact acid molecules. Here we have nitrate ions, and all of those nitrate ions lost their hydrogen ions, making hydronium ions. There aren't any HNO3 molecules in this beaker. Over here, this is HI, hydroiodic acid. There aren't any HI molecules because they all ionized. So this is the weak acid. So determine the hydronium ion concentration in each of these solutions. And what we have to do here is identify, are these weak acids or strong acids? So I'll help you out here and make a list of the strong acids. So those are the strong acids. So this first one, is this a strong acid? Is it on that list I made? No. This is a weak acid. So what that tells me is that when this reacts with water, I'm going to have a double-headed arrow. I'm going to have some hydronium ions being formed. But I'm also going to have a lot of this. So if I'm looking for the hydronium ion concentration, I'm starting out with 0.5 moles per liter of the intact acid. Does all of that form hydronium ion? No, it's a weak acid. So can we actually calculate the concentration? Not with the information I've given you. All we can say about this is that the hydronium ion concentration is less than 0.5. So the hydronium ion concentration is less than 0.50 molar. If this was a strong acid, it would separate completely, and the hydronium ion concentration would equal the concentration of acid. But it's a weak acid, so it's less. That's all we can say. In Chem 1B, you'll learn a lot more about how to do that, and you could calculate that. Let's turn to letter B here. Is this a strong acid? Yes. So when a strong acid is put into water, it reacts completely, forming hydronium ions and iodide ions. So we started out with 1.25 moles per liter of HI. All of that reacted. So if you think of a pair of shoes, a left shoe and a right shoe, and we're taking all the pairs of shoes apart how many left shoes do you have? The same as the number of pairs of shoes, right? And the number of H3O plus will equal the number of I minus because they came together, right? To get these, you have to take one of those apart. Here we're taking all of the pairs apart, and so the concentration of this is equal to the original concentration. For the weak acid, this is, again, we could think of that as pairs of shoes, but only some of the pairs are going to come apart. The rest of them are still in their boxes. So then you look at, well, how many single left shoes are there? Well, it's less than the total number of pairs. How about 0.75 molar HF? Is that a strong acid or a weak acid? It's a weak acid. It's not on the list. Okay? Weak acid. So, I mean, we could write this out, but we don't really have to. Does that completely ionize? No. So the ions that are formed are lower in concentration because it doesn't completely ionize. Does anybody have any questions?
Are we going to have that list on the exam?
I will give you that list on the fifth exam. Yeah. So that was strong and weak acids. What about the bases? A strong base is just one that dissociates completely. So any of the metal hydroxides are going to be considered strong bases: lithium, sodium, potassium hydroxide. The diprotic acids will ionize in individual steps, 2 steps. The bases that have 2 hydroxides, like these guys, strontium hydroxide, they just dissociate in 1 step. So if you have strontium hydroxide, it ionizes, well, it doesn't ionize, it dissociates into strontium ions and hydroxide ions. So if you put sodium hydroxide in water, it separates into ions. A weak base is like a weak acid. It does not completely form into ions. So most common weak bases are going to produce hydroxide by taking a proton from water. They're not going to be a metal hydroxide. You're not going to look at the formula and say, oh, that has hydroxide in it, that must be a base. And so the only one that I need you to remember is ammonia. Ammonia is a weak base. It reacts with water. Water acts as the acid. Ammonia acts as the base. It takes a hydrogen ion from the water. But this has a double-headed arrow. This is a weak base. So there's intact ammonia molecules as well as ammonium ions. So here we have the ammonia molecule. We dissolve that in water. And some of them form ions, but a lot of them do not. It's a weak base. There are lots of weak bases. This is the one that I want you to remember. Organic amines are weak bases. Those are all variations of ammonia. So these all have nitrogen in them. And instead of 3 hydrogens, they've got other things. So they're relatives of ammonia. And the other one that can act as a weak base is the bicarbonate ion. The bicarbonate ion can react with water and take a hydrogen ion from the water to form hydroxide ion. There would have to be something else in there with the bicarbonate ion. Does bicarbonate look like it could act as an acid? Does it start with hydrogen? It does. Bicarbonate ion can also act as an acid and donate a hydrogen. So bicarbonate is an acid and a base, either or. It's amphoteric. And that's why we have shakers of sodium hydrogen carbonate, baking soda, in the lab, because you can use it to neutralize an acid or a base. Now, it's going to be better at neutralizing acids, but it can neutralize bases as well. Okay, determine the hydroxide ion concentration in each solution. So, barium hydroxide, is that a strong base or a weak base? All metal hydroxides are strong. So that's a strong base. When you put that in water, well, you're going to get barium ions and 2 hydroxide ions. And it's going to go completely. It's a strong. It goes completely to the products. So if I have 0.055 moles of barium hydroxide per liter, how many moles of hydroxide do I have? Is it the same?
Yes.
If I take one of these apart, how many of those do I get? 2. So there are 2 hydroxides formed for every mole of barium hydroxide. So you can write this equation showing how it forms the ions, or you can get this relationship just looking at this formula. There are 2 OHs in every one of those. So this will actually generate twice as many hydroxide ions as the original. So 0.11 moles per liter hydroxide ion. Or we can say OH minus equals 0.11 molar. Let's skip that middle one and go to the bottom one. Sodium hydroxide. Is that a strong base? Yes, it is. It's a metal hydroxide. How many hydroxides are in 1 unit of sodium hydroxide? Just 1. So this will form 1 mole of sodium ions and 1 mole of hydroxide ions for every 1 mole of this. So we could write it out like this, or we can just say the hydroxide ion concentration equals the concentration of the base. Where you have to be careful is when you have the OH2, because then the hydroxide ion concentration is actually twice as large. Okay, this one. Does that even really look like a base to you? Probably not. You see this nitrogen here? So I wouldn't give you this on an exam, but here you could go look in the table and see that that's pyridine. That is a weak base. So the weak base in water only goes partially. So we could finish that equation, but that's kind of icky, right? This is a weak base. So what does that tell us about the concentration of hydroxide compared to 1.05? It's less. So the hydroxide ion concentration is less than 1.05 molar. Any questions?